All right, so here's an example of a type of question that you can encounter in calculus. And I want to go through how to solve this with what I call the N.E.R.D.S method. And N.E.R.D.S is an acronym that stands for Notation, Equation, Realize, Derivative, Solve. And it's a nice way to keep track of what you're doing and to keep things organized. So here's our question. It says, as an aircraft is flying at an altitude of 4 miles at a speed of 800 miles per hour in a direction away from a tracking station on the ground, how fast is the angle of elevation changing when the aircraft is over a point 10 miles from the station? So let's start with our notation for this question. I like to draw a diagram of what's going on and make sure that any numbers that are going to stay the same the whole time are going to be numbers on my diagram, and anything that's going to be changing is going to get a letter on my diagram. That's the first part of doing a notation. So the N here for notation means we'll draw a diagram like this to show what's going on. We have our angle theta is going to be changing. You can see that as the airplane is going away from the tracking station, the theta angle is going to be decreasing. It's going to get less and less, even though the height, the altitude, will remain at 4 miles for the entire flight. And we have a right angle on our triangle. Also, this x distance is going to be getting larger and larger. So that bottom leg of the triangle will be getting larger and larger as the airplane flies away. So to continue our notation, I like to show that what I'm looking to find, d theta over dt, and I just say that's going to equal question mark, because I don't know that yet, and that's what I'm looking to find. But I do know dx over dt, the rate that the airplane is going, will be 800 miles per hour. So that means x is going to be increasing at that rate of 800 miles per hour. And then I can also say, I know that tangent of theta, and this is my equation part, E for equation, tangent of theta is always going to be 4 over x. Now that's a nice equation, but what I'm really interested in is what happens to theta and d theta over dt. So I'm going to solve this equation for theta, and now I'm getting into the realize part. I'm realizing that if I solve for theta, then this will start to work out more simply for me. So theta is just going to equal the inverse tangent, or the arctangent, of 4 over x. And now I have an equation that I can take the derivative of, and then I can solve for what's going on. So let's take the derivative of our equation that we have right now. In order to take the derivative of something like this, anytime I have a fraction like 4 over x, I first like to rewrite that in just a different format. I'll rewrite that fraction as 4x to the negative 1. So that that's a simpler derivative to take. So now d theta over dt is what I want. And I notice this is not a derivative with respect to x. It's a derivative with respect to theta. So we're going to do the derivative of the outermost function, the arctangent function. And I've shown in a previous video the derivative of arctangent to be 1 over 1 plus the angle squared. So we're going to get 1 over 1 plus, and then our 4x to the negative 1 will be squared. But because I have an inside function here, I'm going to be using the chain rule and multiply times the derivative of what was inside. So I'm going to have times negative 4 x to the negative 2. But then you'll also want to notice that x itself is a function of time. X up here is actually changing with time at a rate of 800 miles per hour. So we could say that x equals 800 t. 800 miles each hour is how much that's going to be increasing. So the derivative of our inside function here with respect to t is going to be 800. So now we have a full expression of what is going on, the derivative with respect to t. All right, now all we'll have to do is plug in our values for x. Now, in the question, it said that we want to look at what happens when t equals 10 hours. So notice that when t equals 10 hours, x will be 8,000 miles. So we're going to put in 8,000 for both of these values, and we plug that into our handy-dandy calculator, and we will get negative 0.00005. And the units there would be radians per hour. So I would say that that angle is decreasing at not a very fast rate, but you have to imagine at that point the airplane is 8,000 miles away from the original station. So it is a very nice, appropriate answer. I hope that helps walk you through how to do the N.E.R.D.S method for solving this type of question. And it is a nice use of the derivative of the inverse tangent function, which I have another video about if you're interested.